Hi everybody, Dmitry here. In this video we'll have a quick look at 2D processing, more simplified pipeline that can give you much higher resolution data just for if you're interested in 2D scans. As we look here in the previous video, we got our model, but it was not scanned to get that high quality geometry there, but all that could still be used for 2D material reconstruction. So let's go ahead and close this file. One thing that we can get from this process, because it used markers at this stage, is that we know that the distance to our prop was 50 centimeters, so to be precise 505 millimeters, and the exposure compensation was 1.56. So we will remember these parameters when setting up our 2D simplified processing shortly. So if we go back to props, we have this other template for 2D material processing, so we can go ahead and copy paste it, and let's call it chart 2D, so we know that it is going to be a 2D process. So in this case, let's go back to our captured folder and grab the first this frontal facing part of the scan. It's almost, I think the other ones are more rotated, so this is the ideally you would want to make it as camera facing as possible, close to that. I think it's a bit rotated, but that's still good. So let's grab our full sequence that has parallel polarized shots that have specular in them. I like to call them specular polarization, even though that's an incorrect term. And the other ones would be diffuse polarization that doesn't have the specular. In this case it's cross polarized. Let's copy that, go back to our props chart 2D. Let's paste that under EOS folder. Let's click this fold script. That will just quickly organize it into and put it into a single folder. We also run this generate PG image script. In this case it will generate the same data as for our like 3D props, but it's mostly used for other housekeeping things. So in this case we don't have to use any photogrammetry package, but we need to use some information about the scene. And if we, as you can see here, we don't have any registration information or any geometries, but we have the script generate 2D, and that's a helper script that can basically generate all that stuff for us that our inference engine can read and work with. If we run it, it would complain that the distance to plane in millimeters is not specified, and that's what we would either typically use some other markers prior to scanning so that we can estimate the distance, or we can just use a ruler tape to measure that distance to the plane from the camera to the scanning plane. In this case, from the previous process, we know that it's around 500 millimeters. So let's go ahead and edit this file, and here's this variable distance to plane in millimeters, and let's write 500 in here. And now if we click and run the script again, it got some EXIF information, so it knows it's 55 millimeter focal distance. From our earlier videos we know that in reality it's like 61 something here for this lens at that distance, but for this process it's not important because we manually specified this distance. And it also here wrote us that it generated all other files that we're going to look at right now. So now if we go back to the solve folder, in parameters we don't need to now deal with all the scales because everything is in proper units at this point, but we still need to specify this exposure value. From the previous process we know that it should be 1.56, and but sometimes that information might not be available, and we have also separate set of videos where I go ahead and explain how we derive all these parameters here. In this specific case, let's just type in 156, hit save. We have now here two folders: preview, that's going to quickly build the whole data set in a quarter resolution, well, I should say quarter dimensions. So it will take original shots and downsample it 4 times in each dimension, and this is useful when we just want to quickly preview and make sure that everything looks good there. So in this case, let's just go ahead and run it. It should be pretty quick at this point. We can see that there's 12 SPPs, so it used all 12 data samples for the whole set. It's pretty useful for a lot of relatively rough materials, but you have materials, and if you experience a lot of kind of if you have something more smooth and experience these issues with highlights, we have ways to deal with that as well. So at this point, there is no need to do all that image albedo fix up and transfers. We don't really need AO here. We just can go ahead and open our scene in Blender, and here you would see that it's already set up as a 2D object, and everything there is perfectly flat as what we would expect. The only thing here right now is, as I said, the resolution of that is pretty low. It's a quarter size, but we can quickly move our light around and see that, yep, we have a lot of very useful action there, and it looks pretty good there. So at this point, yeah, we can save it and go ahead and build our full res one. Go ahead, build. So this will take a bit longer, maybe about a minute or two, but in this case we would have perfectly like pixel resolution of our original images materials. So you can see here it goes a little bit slower, but eventually it will finish the job. And also one thing to look at is this SPP, that sample per pixel metric, and the larger this number in general case, the better. And as I said, for relatively rough materials, even like flat pieces of leather, all the fabrics, if everything is perfectly aligned to the camera and it's flat, you can get away with just a single shot material scans, no issues. But if you deal with something that's more like less flat surface with a lot of curvature, with a lot of highlights there, and smoother materials, then the only reliable way to do it is to significantly increase the number of lights or a number of perspectives. So in that case, you would basically need to move camera around and treat it as a pretty much like a regular 3D prop, but then build the whole thing just on a plane, and that way you can sort of get away with fewer lights and to get higher quality material definition there. It's getting finished. As you can see, also it read 24 images there, 60 megapixels each, and it's getting finished. And in this case, we're also going to build our displacement map. So at this point, it saves all the data Regarding the colors, that we get asked a lot, what color space we use. It's the original color space of the source footage. So if you shot with, like in sRGB, the output is going to be sRGB color primes. If it was Adobe RGB, then it's going to use Adobe RGB primes in the output, albedo output. So in this case, it's whatever the input color space is, it's the same. The output is going to be in the same space. So the core of the inference is done. The raw images are generated at this point, and here we're just doing various dilations and some outlier fix-ups and things like that. Mostly all the housekeeping stuff that's handled by the all that Python scripting and basically infrastructure scripts. So there you go. It took about 3 minutes 17 seconds. In this case, we can open our model already, and it will be, the scene right now is getting set up. Everything is set up right now, and in this case we're going to get all our original resolution materials in here, and you can see like all that paper and this kind of embossed plastic that looks pretty cool. So if we align to the camera and grab one of the lights, we can also go ahead and start moving it around, and you can see like all that great detail in there. And in this case, in this script, in this preset, as we look in the previous example, if we go ahead and go to params, that parameter that I talked about, this end transfer radius, it's already disabled. So that's already taken care of in here, so we can just move lights around. Let's go ahead and switch to regular view and look at our photometric normal that has all that great detail in there. That's our albedo, that's all in original resolution. We got our roughness, we got our reflectance, color of all that stuff. So right now here that might look a little weird, but when we deal with cross polarization, sometimes that is not 100% effective, and you get some leakage between specular and diffuse. Like in this case, you get the specular, and you could see that there is some coloration there. Some of that is legit and some of that is not, because even when you deal with something, let's say like a fabric that has light coming through all those little fibers that are almost like a glassy kind of cylinders, light gets colored a little bit, then it leaves the fiber, then it hits another fiber underneath it and reflects back into the camera. And in that case, when we look at that integral view from the camera of all that lighting, we essentially see that something that's view dependent and behaves like specular would get that coloration. So even though technically and physically in dielectrics you would not have that coloration, but in practice you do have that. And you would still have cases where light enters the media, it doesn't get scattered too much in terms of direction, and it would leave right away before like other rays proceeding deeper into the material and losing all that polarization. So there is some residual polarization there left that can account for this color. And I also have a separate video talking just about that whole cross-polarization issue. So some of this coloration in here is legit, other one is a bit less legit. But if we look at our like classical things like this black paper or black plastic and most of other things, those would be pretty much black and white and no coloration there. And on some of this color, some of that color is legit. If we switch to our confidence map in here, it doesn't really make much sense because it's only taken into account when we deal with multiple camera perspective. So in this case it looks like an old TV screen, but in this case don't pay attention to that. That doesn't too much there. So that's our high quality 2D material scan, just using original shots without using any photogrammetry software at all. You might say, well, how do we get the distance? And the distance could be measured. And another thing, as we build this full res one, we can also go ahead and build our displacement map as well. Let me run the process. This will take a while, but in this case we generate perfectly accurate displacement maps in proper units, and there's a way to convert between them, but essentially you could go ahead and build completely your own whatever geometry in any 3D package, then project it into a plane, and then use that normal to reconstruct displacement. And when you go back to that package and tessellate the mesh and displace it, you're gonna get the exact match there. So we know that this process would produce you the accurate and exact displacement, even though if you go ahead and try to build something like 60 million points, like polygons in something like Blender, the editor will die. So but if you're using something like ZBrush, then you can get away with those things. So right now, while it's building and finishing building our displacement map, let's go ahead and run Open Photoshop, where we can look at our displacement that we built. By default, we're gonna save it into 16-bit PNG, and like out of the box that might look like muted and not having much detail. You just need to crank up the contrast. So the values that are stored in there by default are divided by 1 by 256. So there you go, the displacement is built, and we have our PNG file over here. So if we go ahead and open it here, that's going to be our displaced plane there based on the normal. And as you can see, if we really want to look and extract all of that detail there, we can just go ahead and under high pass specify, like, maybe, I don't know, like well, 16 was good, 16. And then with curves, if we put that on top, we could adjust the contrast, and we could see that we do have all that data available in there. It just, when you drop it into your 3D package, it's biased around 0.5 there, and then you need to crank up the scale accordingly. So, but as you can see, all that information is in there, and it's perfectly accurate there. And even on these things, we have that as well. So I can go ahead and crank it up even more, so we can reveal all that micro displacement that's available there. And while we have this Photoshop open here, I'm going to, even though we have videos that go into more detail on how to set up that exposure compensation, but since we have Photoshop open, let me go ahead and under preview, let's go and clean everything here. Okay. Yep. Let's also remove this model, and under solve params, let's assume that this exposure, we did not know that, so it was 0 here. So in this case, we go ahead and build this preview. We still know the distance to the plane, that was 500 millimeters or 50 centimeters, but we didn't know the exposure. And as I said, like, when we take pictures, we don't want it to be perfectly exposed or correctly exposed, because we want it to be underexposed to avoid highlight clipping. So in this case, we just build it as is without any correction, and open this albedo map in Photoshop, and we can see that it's pretty dark. and in the video where I talk about all this cross polarization, we know that this particular chart is going to be the basically the 50 D.5 chart. It's supposed to be when we don't use any cross polarization. That should be in lab space, the value around 50 to 51. So in this case, let's go ahead and calculate the average, so it's easy to look at it. And now when I hover my mouse over it, cursor at the top right there, you can see that the value is 25. And the idea is that in cross polarized version, the value there should be between 40 and 42, whereas if it's not cross polarized, that for normal exposure that would be around 50, because if you add specular on top, they will add up. So let's grab this exposure node, not node, but adjustment layer. Not select the area, but I'm going to adjust the exposure, and this texture is generated in sRGB space, and when we adjust this exposure, this adjustment node already takes care of that color management for us, so we can use this exposure as EV value in our tool sets directly. So here I hover it again, it says 31. Then I move it again, now it's 35. So one useful thing, I usually leave a cursor over there, then hover the mouse over that chart and press the up button. Up, and I do that until it's around like 40, between 40 and 41. So something like that. So we can also see that the white balance is not set up like 100% right, so there's a bit more blue, and this is something that we usually do later on as a post-processing step, because when you work with an image, with the JPEG images on the camera, you try your best to set it up all the white balance the best you can, so the source image is close to perfect white balance as possible, but still there's no way to specify custom color profiles, so whatever comes out of camera in the form of JPEG will have colors that are a bit off. Like here, blues are a bit off, the white balance is a bit off, but that's a whole different topic for tutorials and how to do color correction here. Anyway, we got value to around 40, and what we can see here is that it says 1.5, maybe I can push 1 to like 41, so 1.53. And if you remember, before we set it to like automatically from photogrammetry process and our automated marker pipeline, it calculated as at 1.56, so that's close enough. So in this case, as you can see, we basically adjusted it until we got the right value there in lab space. The reason I'm using and referring to lab space, that L value up there, is because in Photoshop and in many other packages like GIMP, you would have color management sometimes enabled, sometimes not enabled, and when you're in different color spaces, if you only look at RGB values, there are a bunch of different settings in Photoshop where it can show you different values there depending on those settings. However, this lab one, it's kind of standard thing, and it's more reliable when you work in this color managed spaces in all these tools. So that's why just try to memorize and work with these values in lab space, because there's a chance that the chances they're making a mistake there are a lot less. So anyway, 153, and that's how we do this exposure. So now imagine when we're about to go and scan some 2D flat materials, we would always start with a color chart, and then we would reuse the same camera settings for all other shots, and then we use color chart to do this calibration. So now we know what the proper exposure value compensation is for these types of camera settings, and then we can go ahead and reuse those settings for other things. So in this case, case, yeah, we basically ended up calculating the same values pretty much as we had there before, and this is how it's done. So and the process is very similar for pretty much the same for 3D props as well, where you would build it, then you would define that in your texture, you adjust, you figure out how much to adjust it, and would use that value, then go ahead and now clean everything there, and that's it. It's clean, all the textures are gone. But when we go ahead and build it now, it will reuse that parameter, and in this window, if we scroll up, we will see their exposure value 1.53. That's what we specified. Let's create a copy of these adjustment, and let's wait until it's finished. So finished. Let's go back, and now let's open our new corrected one in here, and we would see that the value is around 40. It jumps back and forth a bit, and that has to do with the fact that there is some noise there. So that's why usually when I do that stuff, I try to do the average there. So there you go, we got 41 there, and now this one is properly exposure value corrected. And that exposure value correction is not only needed for to get the proper albedo, but also other maps. Reflectance and roughness also rely on that setting the proper exposure. If it's not set correctly, then those values might be quite a bit off, and you might end up with object that looks too smooth, or like wet surface, or too rough, and so on and so forth. So this step is quite important in the whole photometric process. I think everything is pretty much covered at this point, and this will conclude our video that covers simple 2D material processing pipeline. A bit more expensive, not expensive, but advanced one that we'll be talking about has to do more with extra steps that involve flat field correction, and that has to do with the fact that sometimes when we scan these images that are closer to the camera and extend further away from the central line here, you would also have some spots from lights that affect the whole thing, and you might have lens vignette effect that might also affect that thing. So in this case, because we scanned the whole prop, it's relatively far away from the camera. It's also relatively small area in the middle of the lens, so most of those effects could be ignored for this type of scan, and so that's why we can in many cases just can get away without doing all that more expensive in terms of more advanced processing that has to do with flat field correction. And in those cases it involves also scanning basically large wide surfaces at different distances to build in that light distribution, and along with all those lens vignetting effects and correcting for all that stuff.